There are wind turbines across Europe and North America shedding blades right now, not in catastrophic storms, not in conditions outside their rated operational parameters, in normal wind at normal speeds, on turbines that passed every inspection their operators scheduled and every certification standard the industry wrote for itself. In January 2026 alone, 3 separate blade detachment incidents were documented across United Kingdom wind farms, each generating the kind of local news coverage that disappears from national feeds within 48 hours. Each attributed to material fatigue, each filed and forgotten. The blade on a modern utility-scale wind turbine is between 150 and 300 feet long. It weighs between 15 and 30 tons. When it detaches at operational speed, it does not fall, it travels. Documented debris fields from blade failure events extend up to 1,500 feet from the base of the turbine. The industry standard safety setback from residential property in most jurisdictions is 1,000 feet. The math on that particular gap is not complicated. And while the wind industry processes $100 billion in annual global revenue from turbines that are now demonstrably failing faster than their design specifications projected, a Scottish engineering firm named Katrick Technologies has spent the last several years developing and testing a wind energy device with no blades, no rotating components, no gearbox and no tower, one that generates electricity from the same aerodynamic principle that causes flags to flutter and bridges to oscillate, capturing energy that conventional turbines ignore entirely and doing it from a flat panel that a maintenance crew never needs to climb 300 feet to service. The wind industry has not embraced Katrick Tech. It has not funded it, scaled it, or integrated it. It has done something quieter and more familiar. It has ignored it with the specific, deliberate, well-funded quality of silence that $100 billion industries deploy against technologies that make their existing infrastructure look like exactly what it is: expensive, dangerous, and increasingly obsolete. This is the story of why wind turbines are falling apart in 2026, what the industry knew and when, and the bladeless technology that the people profiting from blade replacement would prefer you never learn exists. Before we go any further, if this is the kind of knowledge that should never have been buried, hit the like button right now and subscribe to Lost Tech Vault. Every video we publish here is a door they spent money keeping locked. Subscribe and ring the bell so you never miss the next one we open. To understand why blades are failing now, you need to understand what the wind industry promised versus what physics was always going to deliver. A utility-scale wind turbine blade is an engineering object of extraordinary complexity. It is not fiberglass over a simple frame. It is a precision aerodynamic structure combining carbon fiber, fiberglass laminates, balsa wood core sections, epoxy resin systems, and lightning protection conductors, assembled by hand in molds, cured under controlled temperature and pressure, and finished to aerodynamic tolerances measured in millimeters. The manufacturing process is closer to building a commercial aircraft wing than pouring concrete. And like an aircraft wing, every blade operates under continuous cyclic stress, flexing, twisting, and loading with every rotation, every wind gust variation, and every turbulent air encounter across its operational lifetime. The industry promised operational lifespans of 20 to 25 years. It certified turbines on the basis of fatigue modeling that assumed relatively uniform wind loading over that period. It sold those projections to governments, pension funds, and energy utilities that structured financial returns around them. What the industry knew, and what independent structural engineers had been documenting in peer-reviewed literature since the early 2010s, was that real-world wind loading conditions are substantially more variable and substantially more damaging than the modeling assumed. Leading-edge erosion from rain, insects, and particulate impact degrades blade aerodynamics within 5 years of installation, increasing turbulence-driven stress loads. Internal adhesive bonds between blade shell sections develop microcracking under thermal cycling that inspection protocols relying on visual examination cannot reliably detect. And the cumulative fatigue damage model underpinning the 25-year lifespan projection was built on laboratory data, not field measurement across the actual wind variability profiles of operational sites. The blades failing in 2026 are not failing because of exceptional circumstances. They are failing because the physics always said they would fail at roughly this point in the operational cycle of the first large-scale turbine build-out, and the industry built its financial projections on models that said otherwise. Katrick Technologies was founded in Scotland with a specific engineering premise that the wind industry's entire infrastructure investment makes it structurally incapable of accepting. The premise is this: conventional wind turbines capture kinetic energy from wind by intercepting it with rotating blades. The rotation drives a generator. The process is mechanically elegant in concept and mechanically brutal in practice, requiring precision gearboxes operating under enormous torque loads, blade pitch control systems exposed to continuous weather, tower structures tall enough to reach wind speeds that justify the installation cost, and maintenance programs that require specialized technicians performing inspections and repairs at heights that make the work expensive, dangerous, and dependent on favorable weather windows. Katrick's technology operates on an entirely different aerodynamic principle. When wind flows over and around a flat panel or foil structure, it creates oscillating pressure variations, the same aerodynamic flutter phenomenon that causes flags to wave, that destroyed the Tacoma Narrows bridge in 1940, and that aeronautical engineers have spent decades learning to suppress in aircraft structures because of the destructive energy it contains. Katrick's engineering insight was not to suppress that flutter energy, but to harvest it. Their panel array converts the oscillating pressure waves generated by wind interaction into electrical current through piezoelectric or electromagnetic transduction, capturing energy from wind that flows around a structure rather than through a rotor. The implications of this architecture are significant enough that the wind industry's silence around it begins to make complete financial sense. No blades means no blade erosion, no blade fatigue failure, no blade replacement costs that independent analysts estimate at $200,000 to $400,000 per blade on utility-scale turbines. No rotating components means no gearbox failures, the single most expensive maintenance event in conventional turbine operation, averaging $300,000 per incident. No tower means no tower foundation costs, no tower fatigue assessment, and no 300-foot maintenance access requirement that makes conventional turbine servicing one of the most hazardous occupational activities in the energy sector. The panel arrays Katrick has tested operate closer to ground level, in lower and more turbulent wind conditions that conventional turbines cannot efficiently exploit, across terrain profiles and urban environments where tower-mounted rotors are impractical or prohibited. They scale modularly, they install without heavy lift crane equipment, and their failure mode, a panel losing efficiency, is not a 30-ton blade traveling 1,500 feet through a debris field. The documented performance data from Katrick's testing phases, published in their technical literature and referenced in independent engineering assessments, shows energy capture, efficiency in turbulent and low-speed wind conditions that conventional blade turbines cannot match because their operational physics requires relatively smooth, high-speed laminar flow to function near design efficiency. Below roughly 8 miles per hour of wind speed, a conventional turbine produces minimal power. Katrick's flutter-based panels begin generating at wind speeds closer to 4 miles per hour, the kind of gentle, variable airflow that exists across the vast majority of inhabited land on Earth that is currently excluded from wind energy development because tower turbines cannot economically operate there. This is the part of the Katrick story that the $100 billion wind industry finds most threatening. Not that bladeless technology might eventually replace utility turbines in high wind corridor installations. Rather, it makes viable an entirely different wind energy geography, rooftops, urban installations, low-wind rural areas, and distributed small-scale generation that bypasses the utility-scale project financing, grid connection infrastructure, and industrial supply chains the existing industry controls entirely. A technology that generates electricity from a flat panel in a gentle breeze on a rooftop does not need a $300 million offshore installation contract. It does not need a transmission line. It does not need a crane operator, a blade inspection team, or a gearbox replacement budget. And what does not need those things does not generate revenue for the companies that provide them. I want to be direct with you because this story deserves precision alongside its urgency. Katrick Technologies is an early-stage company. Their technology has been tested and the results are documented, but utility-scale commercial deployment has not been demonstrated at the level that would satisfy grid operators making billion-dollar infrastructure commitments. The efficiency metrics in turbulent conditions are promising, but not yet benchmarked against mature blade turbine performance across full operational cycles. These are real limitations, honestly stated. But the blade failures happening right now across the United Kingdom, Germany, and the United States are not limitations. They are consequences. Consequences of an industry that built financial projections on fatigue models it had reason to doubt, sold 25-year lifespans that physics was not going to honor, and responded to the emergence of a fundamentally different wind energy architecture with the silence of institutions that have too much invested in the wrong answer to ask the right questions. The Tacoma Narrows bridge collapsed in 1940 because engineers built a structure that flutter energy destroyed. Katrick Technologies looked at that same energy and built a device that harvests it instead. The blades are falling, the patents are filed, the physics is documented, and the $100 billion industry replacing those blades at $300,000 each would very much prefer that you keep watching the debris fields and never ask what a panel array on your rooftop might have cost instead. Subscribe to Lost Tech Vault. Share this with someone watching energy bills climb while 30-ton blades travel through safety setbacks the industry wrote for itself. The next vault opens soon, and what is inside it is heavier than this one.